Hey everyone, and welcome back to Central Physics Reviews. In this episode, we're still talking about forces, but we're going to take the laws of physics that we discussed in the last episode, which really represented interactions between small point-like particles, and we're going to see how they apply in the real world, where the systems we encounter aren't small point-like particles, and in fact are combinations of countless numbers of them. So here's an example of an interaction between two systems, each comprised of many particles, right? So one system we have is the Earth, and one system we have is you sitting on the surface of the Earth, which I've represented as a smiley face because you're watching this video, you're obviously smiling and super excited about learning physics. Now, let's say we're interested in tracking the evolution of the state of you, or your body, if you like, right? So that little smiley face is what we're going to call our system, and the Earth is going to be external to the system, but interacting with it gravitationally. Now, in principle, what the process of physics that we just discussed tells us to do is to go through one by one every single particle that the Earth is made of and calculate its gravitational pull on every single particle inside your body. And then if you add up all of those forces and divide by the mass of your body, then you will finally end up with the acceleration that the Earth is going to be pulling you with. But obviously that's not practical in this case. So what we can actually do is make use of a mathematical theorem, which goes by the name of Gauss's Law, which tells us that the gravitational pull from a spherical or roughly spherical object is going to be equivalent to, so let me draw this arrow here to indicate that it's equivalent to, the pull from a single point. So we make that a single green point at the center of the object. So if this was the Earth before, then let's see if I can make that right in the center. So if that was the surface of the Earth before, then we can treat the Earth as a single point located at its center and pretend that all of the mass of the Earth, so let me write down mass of the Earth here. So we can pretend all of the mass of the Earth was concentrated at that one central point, and it turns out that we'll get the same answer for how that one point pulls on your body. So let's not forget to draw your body here, right? You're the nice little happy face sitting on the surface of the Earth. But we can't forget that your body itself, the system that we're interested in, is also made up of many particles. So really what we have to do is we have to calculate how this point-like Earth is pulling on every particle in your body. But it turns out that that's not as hard as you think it might be. If we start by writing down how the Earth pulls on just one particle in your body, so we could call that F part for the force on one particle, then this just becomes an interaction between two particles. So we're free to use Newton's law of gravity, or F equals g times the mass of the Earth times the mass of the particle, divided by the distance between them squared. And the distance between the center of the Earth and any particle in your body is just going to be this distance over here, right? That's the radius of the Earth. And even if some particles in your body are higher up than others, that's not going to change the overall distance very much. So we can approximate every single distance, regardless of the particle, as the radius of the Earth. So then we square that. And of course, the direction of the force is minus r hat, meaning toward the center of the Earth. So if we want to find the total force on your entire body, all we have to do is sum up all the forces on every particle in your body. So if we throw in a little sum notation over here, and we write sum of particles on the left-hand side, and then I move the right-hand side over a little bit, and we equate that to the sum over all particles of that whole thing, then what we can do is we can pull out some of these constants from the sum. So we get g times the mass of the Earth divided by the radius of the Earth squared in the minus r hat direction. These are all constants that don't care which particle we're talking about. And what we're left with is a sum over particles of the mass of each particle. And by definition, that sum is just the mass of your body, or whatever system we're considering on the surface of the Earth. So we can write this total sum as g times the mass of the Earth times the mass of the system divided by the radius of the Earth squared in the minus r hat direction. And that's a really cool result, because what we've just found is that as long as the Earth is roughly spherical, and all of the particles in our macroscopic system are roughly in the same position, then the total force from all of the particles in the Earth on all of the particles in that system is the same as if we just treated the Earth as a single point at its center, and we treated the system as a single point on its surface. Now, in fact, this argument holds true for any force that scales as 1 over r squared, or 1 over the distance squared. So what that means is it holds true for the electrostatic interaction as well, right? What I mean by that is if you have the Earth as something external to your system and your body as your system, then the force acting on your body due to the electrostatic interaction can also be written down as k times the charge of the Earth times the charge of your body, or the charge of the system, divided by the radius of the Earth squared in the r hat direction, where now the charge of the Earth means you sum up all of the charges of all of the particles in the Earth, just like we did with mass, and the charge of the system means you sum up all of the charges of every particle in your body, right? And we know that because, chemically speaking, all the protons are bound to electrons in equal ratios, the total charge of the Earth and the total charge of your body are both actually 0, which means that this electrostatic interaction between the Earth and your body is going to have 0 force, or is going to accelerate you not at all. Now, in the context of this gravitational interaction, this gravitational force that we found here, there is one little shortcut that's frequently used and often very helpful, which is that if you know you're on the surface of the Earth, right? If the system that you're trying to describe is on the surface of the Earth, and you want to figure out with what force the Earth pulls on the system gravitationally, we've already done that calculation, right? We know that this is going to be the answer. And what people have done is they've actually plugged in these numbers, right? G was just Newton's gravitational constant. The mass of the Earth has been measured, and the radius of the Earth has been measured, and those numbers have been plugged into this equation, and the result is that the force with which the Earth pulls any object on its surface gravitationally is equal to 9.8 meters per second squared times the mass of the system in the minus r hat direction, meaning toward the center of the Earth. So equivalently, that's like saying the acceleration due to gravity on the surface of the Earth, and I should make that really explicit, so I'll write SE up here, because this is specifically for the surface of the Earth, but that's going to equal 9.8 meters per second squared down, or toward the center of the Earth, right? And the reason is that, again, F equals ma, so if F is this 9.8 times m, then the acceleration itself is just 9.8. And that's a reflection of the fact we said before that gravitational accelerations don't depend on properties of the system. Namely, they're independent of whatever mass you're considering, right? That was Galileo's famous experiment. If you drop a heavy object and a light object off the Leaning Tower of Pisa, they will fall at the same exact rate. Okay, so this was one clever way to deal with interactions between systems containing many, many particles. But what if the system that you're trying to describe is interacting with something that isn't a perfect sphere, right? It's amazing that there are so many contexts in which this perfect sphere method actually works and is very useful, but that's not always the case. So let's talk about a few more contexts in which you have interactions between many, many particles, but those shortcuts don't necessarily apply. So here we have a system consisting of a simple box, and it's interacting with 4 different things, right? One of them isn't labeled because one interaction is its interaction with the Earth, right? The Earth is pulling down on it gravitationally, but I didn't label it here because that's a simple interaction that we already know how to calculate the force of. There are 3 interactions here that we haven't really gotten to yet. One is some person pushing on the box. 2 is the ground being in contact with the box. And 3 is a person pulling on a rope pulling on the box. So let's go through these scenarios one at a time and see what we can make of them, see how we can treat them, and figure out what the force is. So in this first interaction here, what actually is going on when a person pushes or puts his weight into a box? Microscopically, what's happening is that all of the electrons on the surface of the hands of that person are placed closer and closer to the electrons on the surface of the box, which is our system. And when this happens, there is a fundamentally different effect from anything we've talked about before called quantum degeneracy, which I'm not going to get into. But the point is that electrons really don't like being pressed on top of each other, and that causes a repulsion between these two surfaces. Now, this isn't electrostatic repulsion. I mean, yes, the electrons have the same charge, so yes, they repel each other electrostatically, but there's also a counterbalancing attraction between the electrons and protons on the surfaces, so that's not what makes the surfaces repel, right? This is a fundamentally different effect, but nonetheless, we know that when you push on something, it moves away from you. And because the effect involves so many different electrons on the surface of your hands and so many different electrons on the surface of our system, it's very much intractable to try to go ahead and calculate it exactly. The best you can do is to ask the person, how hard are you pushing on the box? And the person will tell you, because remember, force is a metric for how hard you push or pull or something. The person will tell you, I'm pushing with some number of newtons. And he can also very easily tell you the direction in which he's pushing. And so the net result is just by asking the person, you end up with a force vector. Maybe in this case, it's a little bit up, but mostly to the right. And you get some magnitude for the force F according to however hard the person says he's pushing, however much force he's exerting on the box. Now, you might think that's cheating, but if you know nothing else, then in order to predict how this box will move over time, in order to figure out its acceleration, you need to just be given the force. Whether it's from the person or from a problem in your textbook, someone has to tell you how much force is being applied in a case like this. Okay, now the second interaction between the system and the floor or the ground or what have you is very similar in nature. It's also a quantum degeneracy effect by which two surfaces repel each other because of those electrons not wanting to overlap. But there's a little bit more nuance here because on one hand, gravity is pulling the system down into the ground, and so there's going to be a repulsion up from the ground due to this quantum degeneracy, right? So that's going to be a force upwards. But at the same time, we see that the box is being pushed and pulled toward the right. And if the ground has any bumps in it at all, if it's not a perfectly smooth surface, then what'll happen is the box will be pushed into some of those bumps along the ground, and it will be pushed into them toward the right. So that means that quantum degeneracy will repel the system to the left. And so we have another force going to the left or against whatever direction this box is being pushed in, if there are any bumps or what have you on the surface. And so the net effect is that the surface will push on the system up and to the left. And again, if you know nothing else, because these forces are so complicated, you have to be told what that force is and what its direction is. Now, the caveat, if you know nothing else, is something that we'll get to shortly, but given that condition, if you really know nothing else, then you just have to be given the force. Now, there's also a bit of vocabulary that goes into this, because people like to give the vertical component and the horizontal component of this degeneracy force different names. So the vertical component, or the component that is perpendicular or normal to the surface, is called the normal force, while the horizontal component, or the component of force parallel to whatever surface is in contact, is called the frictional force, and that's labeled by a little script F usually. And in fact, in most cases, you can think of these forces completely independently, right? You can think of a normal force being a response to pushing your system into a surface, and you can think of a frictional force as a response of sliding your system or pushing your system along a surface. But in total, the interaction between your system and the surface is going to be the sum of those contributions. So in this case, up and to the left. Okay, now let's take a look at this third scenario, because there are a lot of really interesting things going on here. In order to model or describe what's going on, let's draw a really simplistic picture of the rope from the point of contact with the system to the point of contact with the person's hands. And I'm going to draw that really simplistically as a bunch of atoms that are in contact with each other, that are bound to each other through chemical bonds, okay? Now, what happens when you pull on the rope, what happens immediately is the atom all the way on the right, where you're contacting the rope, gets pulled a little bit to the right. And so the system itself, or the rope itself, I should say, looks like a bunch of atoms that are bound together, but then there's this one atom that was pulled apart. And it doesn't like that, right? Because there's chemical attraction between all of these atoms. So the atom that's all the way on the right is going to attract the atom to its left a little bit to the right as well. So now what ends up happening, before the system itself even moves, right? If the particle or the atom that's in contact with the system is over here, and the particle that you moved that's in contact with your hand is over here, then what'll happen is all of the atoms in the rope are just going to get more spread out, because they're each going to want to attract all of the atoms to their right and to their left. And we can actually calculate how much these atoms are attracting each other, because you know that if you're applying a force to the atom all the way on the right, but nothing has moved yet, nothing has accelerated, then the attractive force from the atom to the left has to balance it out, right? It has to be the same exact force to the left. And that attractive force will have the same value throughout this whole chain of atoms. So every atom is being pulled to the right and pulled to the left by the same amount F, which is a reflection of the force that you originally put on just one side of the rope. So I'm going to skip a few here, but eventually what we have is that this atom is pulled to the right with some force F, and of course it's attached to the system. Let's not forget that everything here is attached to the system, and that attachment also pulls the atom to the left F, and then this atom pulls the system to the right F. And so this was a long chain of events, but the end result is that by pulling on the atom all the way on the right with some force F, what you see here is that now there's a force on the system which has that same exact magnitude F. And meanwhile, every atom in the rope is being pulled to the right and to the left by the same amount, so it's not being accelerated, but it's kind of being stretched a little. And when that's the case, we say that the rope is in tension, and it's the tension that applies the force to the system. So sometimes when you see ropes or cables or cords pulling on a system, instead of labeling that force F, it'll be labeled T for tension. But the point is, again, if you go and you ask the person, hey, how hard are you pulling on the rope? What force are you exerting on the rope? The answer they give you will actually equal the force with which the rope pulls on the system. And so we can say that the force resulting from interaction number 3 is equal to the force on the rope that the person says they applied. But basically, if we go back to the main point here, what I've essentially told you is that if you know nothing else, then these complex interactions that don't involve perfect or approximate spheres are basically just going to have to be specified for you. In other words, someone's just going to have to give you or tell you what the force is in order for you to be able to find the corresponding acceleration and do kinematics and figure out how the system will move over time. But actually, in many cases, you do know something else. And to illustrate what I mean by that, let's talk about this example of a rubber duck in a puddle being pulled on a leash. No rubber ducks were hurt in the making of this video, I promise, but this is going to serve as an illustrative example, so let's get into it. So the first thing we do when we want to analyze a system is figure out what it's interacting with in the external world. And in this case, there are 3 obvious sources of interaction. The first is gravity. Presumably this puddle is on Earth, so there's a gravitational interaction pulling the duck downward. So maybe I'll draw like a downward arrow over here and label that 1. The second interaction is going to be the interaction with the ground, right? We know that the surface of electrons on the ground will repel the surface of electrons on the bottom of the rubber duck. And so that's going to create a force upward. And we also see that the duck is being pulled to the right. So we suspect that if there's any friction, that's going to create a force leftward. And so the net effect is that the ground will again be pushing the rubber duck up and to the left. So I'll draw that arrow here and label it 2. And then of course this final interaction is going to be the tension force pulling the duck down and to the right. So I'm going to label that interaction number 3. Now 2 of these interactions are very complicated, right? Namely, the third interaction with the tension and the second interaction with the quantum degeneracy are both complicated interactions that we don't have laws for, right? We don't have an equation for what the force is coming from those interactions. But it turns out that we can actually say something about what those forces are. So for the purpose of this example, what I'm going to do is I'm going to assume that this tension force is actually known, right? Let's say there's a person pulling on the rubber duck, and we ask them how hard are you pulling and in what direction, and they give us a straight answer. So let's say that's known, and let's work to figure out this other complex interaction between the rubber duck and the ground. So I'm going to be super explicit, right? If we know nothing else, then we can't do any physics, we can't do any math to just figure out what that second interaction will correspond to in terms of force or acceleration. But what I mean when I say we know something else is that when the duck is being pulled along this pond, we know that its acceleration vector, if we draw some coordinate axes here, so maybe we call x the horizontal direction and y the vertical direction as is standard, we know that its acceleration vector will have some x component, ax, but we also know that it'll have no y component, right? Its y component will be 0 because there is no interaction that can possibly accelerate this duck upwards. Now you might have to think a little bit to convince yourself of this, because it's true that the ground, or the puddle, is in fact pushing upwards on the duck, but there's actually no way that the duck will accelerate upwards, because if the duck lifts off the ground by any amount, that force will entirely disappear, right? That interaction won't be there anymore. So it can't have any real acceleration upwards. And so equivalently, we can write down that the net force on this duck is going to be the mass of the duck times this ax, whatever it is, and then again, 0 in the y direction, because you can't have acceleration be 0 without having the force be 0 in the y direction as well. Now this actually gives us a lot of information because it constrains what our 3 forces can be, right? They can't just be anything they want. They have to be some combination that adds up to have 0 in the y component. So if we write out the fact that F1, this gravitational force, is equal to 0 in the x direction and minus mg in the y direction. G is the variable that we use to denote the acceleration at the surface of the Earth. So that's 9.8 meters per second squared by definition. Then we can also write down F2 as a vector. We know that it has some x component, which we call friction. And maybe I'll write minus F because we know it's going to act to the left. And we know that it has a y component, which is called the normal force. But we don't know what either of those are. Those are what we're trying to constrain or figure out. And then we can write down F3, which we were lucky enough to get the person pulling this duck to tell us. So we have some tx component and some ty component that we know. So tx and ty are numbers that we know, but the cursive f and capital N are arbitrary numbers that we actually don't know by construction of this problem. And so the process here to make use of the constraint is to actually just add up F1, F2, and F3 and mandate that it equals this total force F that we specified before, right? So in particular, if we sum these vectors, so the sum over I of Fi is going to equal, well, the x component is the sum of all the x components. So that's Tx minus friction. And the y component is the sum of all the y components. So that's Ty plus N minus Mg. And we know that that has to equal the net force, which we said was Max and 0 in the y direction. And so immediately what we find, if we look at the y component of this equation, is that the normal force, which was our unknown in this component, has to equal exactly mg minus ty. so that when you do the sum on the left-hand side, you actually end up with 0. So now all of a sudden, we actually know what the force is corresponding to this really, really complicated quantum degeneracy interaction between the rubber duck and the ground, just by having specified that we know there can't be any acceleration in the y direction at the end of the day. Now, this constraint on the acceleration isn't necessarily something that could directly help us find the frictional or horizontal component of the interaction between the rubber duck and the ground, but in fact, it turns out that if the rubber duck is moving, there is always a linear relationship between those two components of the interaction. So let me write down, for a moving duck, what ends up happening is the value of the friction force is equal to some number, which is called mu sub k, the name is the kinetic coefficient of friction, multiplied by the normal force n. So the stronger the ground pushes up on the duck, the stronger the ground will push left on the duck, assuming the duck is moving. And there's an analogous statement for stationary ducks, but we won't get into that right now. The point is that for a moving duck, just knowing the normal force actually tells us both components, the normal and the frictional components of that interaction. And so we can actually find the acceleration of this duck, even though initially we had no idea what force the second interaction would correspond to. So in particular, if we want to solve for the acceleration in the x direction, let me just erase this for now. So we can consider the x component of this equation now to solve for the acceleration in the x direction, right? So in particular, if we just divide both sides by m, then we can solve for ax is equal to tx minus f over m. And remember that tx is given to us, and f was just mu k times the normal force. So mu k times the quantity that we found before, mg minus ty. And all of that is divided by m. Let me quickly fix that k there. But yeah, there we have it. We started out with a system in which we had a really complicated interaction between the rubber duck and the ground, but just by knowing that there's no way the duck will accelerate in the y direction, that piece of information was enough to let us figure out what that complicated interaction must be in terms of the force it corresponds to. And so that's the second clever way in which you can solve these complicated problems, is by using things that you already know have to be true about the acceleration of your system. So hopefully these examples gave you a pretty good idea of how it's still possible to do physics even in really complicated situations where technically there are countless individual interactions going on all at once. In the next episode, we're going to be talking about energy, which is yet another tool that lets us do physics with systems where tracking each individual interaction between pairs of particles isn't exactly feasible. So if you want to learn more about how to do physics in the real world, I hope to see you there.